In this section, I would like to introduce the transverse internal area and the area of metal items. The transverse internal area refers to the area of the internal cross-section of the pipe where the fluid actually flows. On the other hand, the area of metal refers to the cross-sectional area occupied by the pipe wall, the metal part. These two areas are calculated from the outside diameter and wall thickness data we looked at previously, and they are key values widely used in flow rate calculations and pipe strength calculations.
Now, I will introduce the internal area and metal area columns in the Chapter 11 pipe data table. All area values in this table are expressed in square inches. The transverse internal area refers to the internal area where the fluid actually passes through the pipe cross-section. It is the flow cross-sectional area enclosed by the inside diameter, d. Meanwhile, the area of metal is the cross-sectional area occupied by the metal of the pipe wall, corresponding to the ring-shaped region between the outside and inside diameters. Even for the same nominal size, as the schedule number increases, the wall thickness becomes thicker, which increases the metal area and decreases the internal flow area. This data is extracted from Crane's technical paper number 410, Flow of Fluids.
Next, I will introduce the area of metal column. This value represents the area occupied by the metal in the pipe wall cross-section in square inches. Conceptually, this metal area is obtained by subtracting the flow area based on the inside diameter from the total cross-sectional area based on the outside diameter. The value varies depending on the schedule number and wall thickness, with differences between schedules such as STD, XS, and those for stainless steel like 5S and 10S. In particular, 5S and 10S have relatively thin walls, so the metal area is smaller. This metal area value is used essentially when calculating pipe strength, estimating weight, and evaluating pressure ratings, and it completes the composition of the pipe cross-section together with the transverse internal area column seen previously.
Finally, I will introduce the water weight and inside diameter columns. The water weight column represents the weight of water that completely fills the pipe per foot, with the unit being pounds per foot. The inside diameter refers to the internal diameter of the pipe, denoted by the variable d, and the unit is inches. This d value is a key variable that serves as the basis for calculating the flow area. The larger the inside diameter d, the wider the flow area and consequently, the greater the weight of water contained per foot. Conversely, as the schedule number increases, the wall becomes thicker, the inside diameter d decreases, and the water weight also decreases. This water weight value is used directly in design when calculating the load for supporting the piping or calculating the weight in a water-filled state. For reference, these columns are repeated twice side by side within the same table to improve readability when reading a wide table.
Now, I will introduce the inside diameter item in the pipe properties table. In the table, this column is in inches and is denoted by the symbol d. The inside diameter d refers to the diameter of the passage through which the fluid actually passes inside the pipe. Therefore, this value is used as the most basic input value that serves as the basis for calculating cross-sectional area, flow velocity, and pressure loss. One thing to note is that even for the same nominal diameter, the d value varies depending on the schedule or wall thickness specification. As the wall becomes thicker, the inside diameter d becomes smaller accordingly.
Next, I will introduce the column where the water weight item and the inside diameter are grouped together. Here, water weight refers to the weight of water that completely fills the pipe per foot, and the unit is lb/ft, or pounds per foot. The inside diameter, d, is in inches, and the internal cross-sectional area is determined from this d value. Since water weight is obtained by multiplying this internal cross-sectional area by the density of water, the water weight increases as d increases. This figure represents the load applied when the pipe is full of water, making it very useful when designing pipe supports. If the flowing fluid is not water, you can convert it to the actual filling load by multiplying it by the specific gravity of that fluid.
This slide is a physical properties data table summarizing the physical characteristics of large diameter pipes based on the inside diameter d value. For example, when the inside diameter d is 29.5, the metal weight is 23.37 pounds per ft and the water weight is 296.2 pounds per ft. within the same diameter group. As the wall thickness increases, the inside diameter tends to decrease, the metal weight increases, and the water weight decreases. I encourage engineers to first select the diameter group that fits their design conditions and then directly refer to and utilize the necessary cross-sectional area and weight values.
Next, we turn to flange and bolting.
This slide shows the bolt circle diameter table for American pipe flanges according to ASME B.20.1, B.20.5, and B.20.24 standards. This table illustrates the diameter differences between the Class 150 and Class 300 series. For example, for a 2 inches nominal size, Class 150 is designed at 4.75 inches, and Class 300 at 5.00 inches. Rather than memorizing all the values, please first verify the class and nominal size of the flange you are designing, and then find and apply the corresponding bolt circle diameter. In particular, the application range for cast copper alloy flanges or steel valves specified in the bottom notes varies by nominal size, so I strongly recommend reviewing these precautions during practical application.
As a continuation of the bolt circle diameter table we looked at previously, this section contains diameter values in inches for larger nominal size ranges. For instance, the diameters gradually increase according to the nominal size from 3.50 inches in the medium range up to 39.00 inches in the maximum range. Instead of listing every value, I suggest that practitioners refer directly to the values needed based on their specific nominal size and class. Please note that the triple dash notation in the table indicates that there is no applicable value for that combination, and I recommend reviewing this alongside the stud bolt information for ASME B16.1, B16.5, and B16.24 standards that follows.
This slide is a reference table summarizing the number and diameter of stud bolts according to ASME B16.1, B16.5, and B16.24 standards. For each class, such as Class 125 and 150, or Class 250 and 300, the number of bolts and their diameters in inches are provided as a pair. For example, small nominal sizes like 1 1/4 in start from 0.50 inches, and as the nominal size increases, the diameter gradually expands up to 1 inch, or 2.00 inches. Rather than memorizing all the values, please first check the nominal size and class of the flange you are designing, and then find the appropriate bolt specifications in the table. In particular, the application range for cast copper alloy flanges or steel valves differs as shown in the bottom notes. So please be mindful of this when determining actual fastening specifications.
This slide provides bolt dimension data for American pipe flanges according to ASME B16.1, B16.5, and B16.24 standards. This table shows the correlation between how the bolt diameter is determined based on the nominal pipe size and class rating. For example, while small bolts of about 0.62 inches are used for small nominal pipe sizes, if the class rating increases from 150 to 300, the bolt diameter increases by 1 step even for the same nominal pipe size. For detailed values, please first verify the nominal pipe size and class rating of the flange you are designing, and then refer to the inch value at the corresponding intersection. In particular, the dotted lines on the right side of the table mean that the data is not defined. Therefore, when designing large diameter flanges for high pressure ratings, please carefully check if large bolt diameters of 3.00 inches or more are applied.
Next is the outer diameter data for American pipe flanges according to ASME B16.1, B16.5, and B16.24 standards. This table is divided into the Class 150 and Class 300 series, showing the characteristic that the flange diameter varies by class even for the same nominal pipe size. For example, when the diameter of the Class 150 series is 4.25 inches, the Class 300 series is designed larger at 4.88 inches. I will not list all the values, so engineers should first verify the nominal pipe size and class rating of the piping they are designing, and then refer to the corresponding diameter value. I also recommend considering the application range of cast copper alloy flanges specified in the bottom footnotes.
This table is a reference document summarizing the thickness of flange fittings in inches according to ASME B16.1, B16.5, and B16.24 standards. For the class 125 to 150 series, it starts with small diameter values such as 4.88 inches, while the class 250 to 300 series consists of thicker values such as 5.88 inches compared to the same nominal pipe size. Rather than listing all the values, please first verify the nominal pipe size and pressure rating of the piping you're designing, and then find and use the corresponding thickness value. In particular, please be careful when applying this, as the parts marked with dotted lines in the table indicate that the data for that combination is not defined.
This slide contains the dimension standards for cast iron class 250 and steel class 300 flanges, showing that these two standards are compatible dimension groups. For example, when checking the dimensions for specific sizes, such as a 1 inch or 2 inches, nominal pipe diameter, you will refer to the values designed according to the ASME B16.1 and B16.5 standards. The remaining detail values are organized so that engineers can check them directly according to the pipe diameter they are designing. Please first check the class number in the table header. Then find the dimension value corresponding to the nominal pipe diameter you intend to apply and reflect it in your design.
Next, I would like to introduce the face markings for class 150 flanges. Even within class 150, there are 3 types depending on how the face is machined. First, cast iron class 150 uses a flat face, referred to as FF, which has a flat seat shape. Steel class 150 uses a raised face, referred to as RF, which has a protruding face shape. And RTJ stands for ring-type joint. This is a face shape for steel flanges where a metal ring gasket is inserted for sealing under high pressure or high temperature conditions. As such, FF, RF, and RTJ differ in their joint face machining methods, leading to differences in the types of gaskets used and their sealing performance. In the table, flange thickness and dimensions are listed separately for each face shape. The STL notation at the end indicates that these RTJ dimensions apply to steel flanges.
This slide is a reference table summarizing the dimensional standards for class 150 cast copper alloy and class 300 steel flanges. The key point is that cast copper alloy flanges follow the ASME B16.24 standard and apply to nominal pipe sizes from 1 to 12. For example, these standards are applied when designing seawater or chemical piping where corrosion resistance is critical. In particular, Class 150 copper alloy shares the same dimensional system as Class 150 steel. Please check whether they apply to steel flanges via the STL items noted in the footnotes for detailed dimensions, and refer directly to the values corresponding to the pipe diameter during actual design.
This slide is a reference table summarizing the end-to-end and end-to-face dimensions according to the nominal pipe size, or NPS, for Class 300 steel valves. For example, for the NPS 1 1/4 row, dimensions in inches are defined, such as 0.44 or 0.69, and the values tend to increase monotonically as the pipe diameter increases. Please note that the dotted lines in the table indicate that dimensions for that specific combination do not exist. Engineers should first verify the pipe diameter and the end flange type, such as RF or RTJ, and then apply the correct dimensional data by finding the intersection of the corresponding row and column.
I will now clarify the scope of application for the dimension table we just saw. These dimensions apply to steel valves, and the target nominal pipe sizes are NPS 1 through 24. This means that for any diameter between 1 and 24, you can use the values from this table directly for design or selection. This data is reference material included in Chapter 11, Pipe Data.
In this slide, I would like to introduce the header structure of the Class 300 cast copper alloy valve dimension table. Here, cast copper alloy refers to cast copper alloy, and this table organizes the dimensions of copper alloy valves by pressure class. At the top of the table, several classes or pressure rating intervals are arranged repeatedly, and within each rating interval, the end types are divided into RF and RTJ pairs. RF stands for raised face, meaning a protruding flat flange, and RTJ stands for ring-type joint, meaning a joint where a ring is inserted. This RF and RTJ pair repeats 5 times to represent 5 rating intervals. Meanwhile, the row axis is based on the pipe or pipe diameter. Therefore, to find a dimension, select the desired pipe diameter row from the left pipe column, choose the column from the combination of class and RF or RTJ at the top, and read the value at the intersection of the two axes.
This slide contains the standard data for PN16 cast steel flanges and shows the basic dimensional design principles of flanges according to the nominal diameter. For example, thickness values range from 6.5 to 9.5 millimeters, and as the nominal diameter dn increases, the flange thickness also tends to increase. Since all dimensions are in millimeters, please check the dn value first during design and then sequentially refer to the corresponding outside diameter and bolt hole diameter. I ask that engineers verify the remaining detailed figures directly from the table to suit their actual design conditions.
This slide is a reference table summarizing the detailed specifications of bolts required for flange fastening. It shows the correlation of how the number of bolts and thread specifications are determined based on the bolt circle diameter. For example, thread thicknesses vary from the smallest size, M12, to M56 for large flanges. As the nominal diameter increases, the number and thickness of bolts increase accordingly, so please check the required specifications in this table according to the flange size you are designing.
This slide contains the standard data for PN25 cast steel flanges, which respond to higher internal pressure requirements. For example, if you look at the thickness items, dimensions are defined according to the design pressure, such as 6.5, 7.5, and 8.5 millimeters. All dimensional units are in millimeters, and engineers should refer to the detailed figures directly according to their design conditions. I recommend using the outside diameter and thickness values defined for each DN as a criterion for selecting the flange most suitable for the site conditions.
This slide is a bolt selection criteria table applied to piping flange connections. It shows a structure where the bolt circle diameter, number of bolts, and thread specifications increase step by step as the nominal diameter increases. For example, M12 is applied for small diameters, but the specification expands up to M64 for large diameter flanges. All dimensions are indicated in millimeters, and engineers should check the detailed figures according to the corresponding DN they are designing. When applying this in practice, I recommend reading the bolt circle diameter, number of bolts, and thread specification of each row together as one line to select the correct bolt.
Next is the standard table defining the outside diameter, thickness, and bolt hole diameter for PN40 grade cast steel flanges. You can see a structure where the outside diameter and thickness of the flange increase step by step as the nominal diameter dn increases. For example, thickness is precisely defined as 6.5, 7.5, and 8.5 millimeters. All dimensions are indicated in millimeters, so please check the dn value of the piping you are designing first and then refer to the corresponding outside diameter and thickness figures.
This is the continuation of the flange bolting specifications we saw previously. This table shows the correlation where the bolt circle diameter, number of bolts, and thread specifications increase together as the nominal diameter increases. For example, while M12 is applied for small nominal diameters, you can see that the specification expands through M56 up to M64 in the large diameter section. Rather than listing all the figures, please find the row for the applicable DN during actual design and check the bolt circle diameter, number of bolts, and thread specification as one set. Please keep in mind that all dimensions are in millimeters when referring to this table.
Now, I would like to introduce the components of the standard dimension table for PN63 cast steel flanges. This table summarizes the specifications for flanges manufactured from cast steel. Looking at the main items in the table, first, hole diameter refers to the diameter of the hole through which the bolts pass. DN stands for diameter nominal, representing the nominal size of the piping and flange. Outside diameter refers to the overall diameter to the outer edge of the flange, and thickness indicates the thickness of the flange plate. This thickness is determined according to the pressure rating, which in this case is PN63. Finally, please remember that all dimensions listed in the table are expressed in millimeters.
This slide is a reference table summarizing the bolt circle diameter, number of bolts, and thread specifications required for flange fastening. It demonstrates the principle that larger flange sizes require more and thicker bolts to ensure fastening strength. For example, it is structured incrementally from small sizes like M12 up to fine threads of M72x6. I won't list every single value, so please check the required thread designation and bolt quantity directly according to the detailed dimensions of the flange you are designing.
Lastly, I would like to introduce the thickness and dimension items for pipe flanges. This table summarizes the specifications for piping flanges and follows the same structure as the cast steel flange standard we looked at previously. Hole diameter is the diameter of the hole for the bolts, and dn is the nominal diameter, which serves as the standard for identifying the piping size. Outside diameter refers to the outer diameter of the flange, and thickness means the thickness of the flange plate. Please also keep in mind that all dimensions in this table are expressed in millimeters. With this, we have covered all the dimension item configurations for piping flanges.
Now, I will introduce the standard dimensions for PN 100 cast steel flanges. This table summarizes the standard specifications for cast steel flanges with a pressure rating of PN 100. First, please remember that all dimensions in the table are expressed in millimeters. The baseline value for the dimensions is the dn, or nominal diameter. Depending on this dn value, the outside diameter of the flange, the thickness of the flange, and the hole diameter for the bolts are each determined. In other words, the outer diameter, thickness, and bolt hole size of the flange are all decided at once through the table based on which nominal diameter piping is used.
Next is the bolting specification table for PN 160 cast steel flanges. This table shows how the number and size of bolts are reinforced according to the nominal diameter to withstand high-pressure environments. For example, you can see that while small sizes like M12 are used for small diameters, very large bolts up to M64 are applied as the diameter increases. For detail values, please proceed with your fastening design by checking the pitch circle diameter, number of bolts, and thread specifications in order according to the nominal diameter of the piping you're designing.
Finally, let's look at the connection structure between the flange bolting table and the piping data. This table defines the flange fastening specifications through the bolt circle diameter, number of bolts, and thread specifications. For example, the corresponding number of bolts and diameter are determined based on thread specifications such as M10 or M24. Rather than listing all the values, please first find the required thread specification for your flange rating, and then check the bolting data in that row. The end of this table leads directly into the pipe data section, so I recommend proceeding with your design by reviewing the flange specifications and piping dimensions together.
Now, I would like to introduce the basic dimension table configuration for pipes and flanges. This is a data table that summarizes the outer diameter and thickness of the pipe, as well as the bolt hole diameter used for flange fastening, based on the nominal diameter denoted as dn. The dn in the leftmost column is the nominal size used to identify the pipe and flange. Outside diameter is the outer diameter of the pipe, and thickness refers to the thickness of the pipe wall. The hole diameter is the diameter of the bolt holes used when mating and tightening flanges. One thing you must remember here is that all dimensions in this table are unified in millimeters.
Next is the table summarizing the standard dimensions for PN 250 cast steel flanges. This table defines the specifications for cast steel flanges applied to high-pressure environments of approximately 25 megapascals. For example, the outside diameter, thickness, and hole diameter are each set differently depending on the dn specification. Engineers, please first verify the nominal diameter of the piping you are designing, and then refer to and apply the detailed dimensions in millimeters corresponding to that specification.
Lastly, let's look at the bolt fastening specifications for PN 320 cast steel flanges. This is a standard reference showing how the bolt pitch circle diameter, quantity, and thread specifications are determined according to the nominal diameter of the flange. For example, you can see that thread specifications from M16 to M48 are applied incrementally, depending on the size. Rather than listing all the values, please first check the nominal diameter of the flange you are designing, and then match and apply the corresponding number of bolts and thread specifications.
This slide is a reference table summarizing the bolting specifications for PN 320 cast steel flanges. It shows the design principle where the bolt circle diameter and thread specifications increase incrementally as the nominal diameter of the pipe increases. For example, while M16 specifications are applied for small pipe diameters, you can see that they increase up to M48 as the diameter grows. Since PN 320 is a high pressure rating, it requires thicker and more bolts compared to low pressure ratings, so please verify the exact dimensions for the nominal diameter during design. I recommend utilizing the table by finding the corresponding pipe diameter in each row and cross-referencing the bolt circle diameter and thread specifications.
Next is the table summarizing the dimension items for PN 400 cast steel flanges. Based on the nominal diameter, DN, this table shows key design dimensions such as bolt hole diameter, outside diameter, and thickness in millimeters. For example, the outside diameter and thickness of the flange are determined by a specific DN value. In particular, since PN 400 is the highest pressure rating, you can see that the dimensions are designed to be larger than other ratings. The remaining detailed values are structured so that engineers can refer to them directly during design. So please first find the DN value to be applied and then check and apply the corresponding thickness and diameter in order.
This slide is a table summarizing the bolting specifications for PN 400 cast steel flanges, showing the correlation between pipe diameter, bolt circle diameter, quantity, and thread specifications. In the case of thread specifications, they increase incrementally from the smallest M16 up to M45, reflecting the design principle of ensuring fastening strength and preventing leaks in high-pressure environments. Since detailed values vary by pipe diameter, please first verify the pipe diameter of the target object during actual design and then refer to the matching bolt circle diameter and thread specifications.